everyone. We may start.
All right. Well, great. Thank you. And thanks for welcoming me here. I'm privileged to be here talking to you. I see we've got a small group, and I'll just share my screen. Here we are. And we go. So my name is Nicolas Smoll. Again, as you know, I'm a public health senior medical officer. So I work in a public health unit for the Sunshine Coast. Just briefly, my research interests are both communicable diseases and non-communicable diseases, particular brain tumors, and I did a lot of data linkage work in that field. And then throughout COVID, of course, there's plenty of outbreaks to write about and talk about. So my research is epidemiology, biostatistics, and machine learning, that I used in my PhD thesis. And my interests are in the world of vaccines and outbreaks, because vaccines is a lot of what changes the dynamic of an outbreak. It's one of the key response measures. So very excitingly, Queensland has been one of the states that has best, managed, well, some will argue whether it's the best management, but we had an extraordinary good, effective way of preventing outbreaks. Throughout the entirety of the pandemic, we never really got exposed to the Alpha or Delta variants of COVID-19. And so we opened up just for the arrival of Omicron. A lot of the successes of COVID was through public health measures, closing of the borders, restricting movement, and aggressive contact tracing. So what happened is that the public health review, so they committed to do a public health review to, review the public health units throughout Queensland. And one of the key findings was that we need more public health intelligence. And that was felt by myself and all my colleagues throughout, is that we needed more intelligence, more information that we can make decisions on. And while this is the roadmap, I would just to look down here, that one of the key priorities was to, invest in, information system enhancements and, the developing of dashboards, as we're talking here. The problem with dashboards is, yes, you can put some dashboard, but you need good information inside that dashboard. And one of the major problems that we all well know about is the information silos that we have throughout health. The information silos, by that meaning you've got siloed data, you've got case data, you've got hospital admissions data, you've got vaccination data sitting somewhere else. And it's very rare that we can all put them together. Now, this is where data linkage comes in, and data linkage is one way of putting that disparate data sources together. We know very well that there are, two key approaches to data linkage: deterministic and probabilistic. The probabilistic, I think, is supercharged with the advent of machine learning, and now for deterministic is the one where we very well know is you identify a key, or just for example, if it's a patient ID, and then you can link it to a patient ID if you've got the same patient ID. Sometimes we talk about Medicare numbers, but they're also can be quite problematic. So what we have is, deterministics is very good, computationally efficient. You get few false positives, but your sensitivity is lower. So it means you find fewer matches. So, and that's been demonstrated in some really nice works by Granis. You see reference to down the bottom, and exceedingly good article that really compares deterministic and machine learning in the context that we're talking. So hospital admissions databases. The next one is through the use of machine learning algorithms, which is really nice, except it's computationally expensive, because you got to put every link, you almost got to put every potential record with every potential record, which is exponentially very expensive. But it allows for good matches, and as we'll see later, is better overall outcomes than deterministic, even with supervised, meaning human input, deterministic matches. So the aim of what I'm really talking today is going to be providing real-time intelligence. So public health physicians, so doctors that oversee public health units, pandemic planners, intelligence is one of the key parts of an outbreak investigation. It's key part of managing an outbreak, a pandemic. Our understanding of the burden on hospitalizations is through intelligence, and that's what drove us to decide to close borders, restrict movement. It was based on intelligence that allowed us to implement these measures, because we also had to convince the public. So having really good quality data to make good quality decisions is important. One of those decisions is vaccine effectiveness. So, for example, the Chadox AstraZeneca vaccine, that is now going to be delisted and no longer used, when it was going to be our #1 vaccine to manage the pandemic. But it became obvious that firstly that there was some adverse events, which were probably, in my opinion, slightly overblown. But then there was actually just considerably reduced effectiveness in that category, and we'll see it here today as well. We need to know that early, so that we can stop using it earlier and use better vaccines to manage the disease. So there's three key databases that we're going to talk about today. It's the Notifiable Conditions Register. This contains any notifiable disease in Australia. So, for example, measles is an absolute notifiable disease. COVID-19, absolute notifiable disease. Q fever, salmonella. There's about 75 odd diseases, and then they all enter this. They must all enter this register. And there's not only that, but there's a fair bit of data cleaning that occurs by clinicians. So it's a very high quality data set. The second is the Queensland Hospital Admitted Patient Data Collection. I'll call that the QHAP-DC, or QAPT, is for some other people call it. It's all hospital admissions in public hospitals only throughout Queensland. This is important, and this is one of the key limitations of this study, is that we're only collecting public hospital admissions. It gives you an ICD code. It gives you the costings of that admission. Excellent data set. And then we've got the Australian Immunisation Register. Now, prior to the advent of COVID, there was no mandatory input of vaccination data into the Australian Immunisation Register. The COVID-19 pandemic has changed us and taught everyone that you absolutely must input COVID-19 vaccination data into this register. This is how the government works out what's the vaccine coverage throughout our population. So anyone with a Medicare card will be on the Australian immunization record. So these are the three data sets that I want to do, because the preventable respiratory viruses, as you can see here, are all going to be in the Notifiable Conditions Register. Okay, and that's the top focus of this study, is to really understand the behaviors of these diseases, but also the vaccines that are used for these diseases. But because the information is siloed, we got to bring it together. The ultimate aim of this is a dashboard for clinicians, but also, for real-time data and feedback, but also to monitor vaccine effectiveness. And that's through, design of studies, but also actually put this into the dashboard, so you get real-time vaccine effectiveness. So I'll talk slightly a bit about my methods. So I took the first 4 months of Central Queensland's COVID outbreak data, 4 months between January 1st to April 30th of 2020. So this is about 2 weeks after the opening of the borders. So the borders opened on the 13th of December 2021. We had our first case on December 21, but it was only a trickle. And from January 1st to April 30th, we had quite a significant onslaught. One of the key things when you're linking data sets is what's the algorithm that you're going to use to determine whether a person is identified as Indigenous. So actually, on that note, I did forget to acknowledge our traditional owners. So I would like to take that time to acknowledge traditional owners upon which the lands that this study was conducted, and this was the Darumbal people in Central Queensland. So we use the ever indigenous. So if there's if one data set shows that they're indigenous, that person will be considered indigenous. This is really important, less so for this study, but more so for studies where I have multiple entries of a person, because sometimes they'll identify as indigenous and sometimes not in those data sets, and you've got to make a decision. So here, if it's shown up once in the data sets, we're going to list them as indigenous. Vaccine effectiveness for this study is 1 minus the relative risk, which is very standard. So think of it, you're calculating an odds ratio or relative risk of hospitalization for unvaccinated versus vaccinated people. It's just 1 minus the RR, which will give us a percentage between 0 and 1. You need 7 days post your vaccine to be considered vaccinated, which is pretty standard within the literature. And we allow about 28 days between diagnosis and hospitalization, as well as 7 days before. So you might be hospitalized and then get your diagnosis, and we're accepting those when we do our linkage. This is real critical to determine if a link between a hospitalization and a case is actually true or not, because you might have a person who has a COVID-19 a COVID-19 diagnosis, but then has an admission, or they might have multiple diagnoses, but they might have an admission 6 months later for another COVID-19 reason. So we've got to be careful on our matches for those reasons. So the goal of this project will probably be to be unsupervised machine learning. I was really hoping to do supervised learning using the Medicare record, Medicare card as a gold standard, or our to form our training data set. However, the Medicare numbers were not very good. There's a lot of persons with 2 Medicare numbers, and a lot of them, and not a lot of the people actually had Medicare cards listed in all their data sets. So we, in terms of creating the comparisons, it was difficult. A lot of that's because you get multiple Medicare numbers, because children who live with divorced parents, they can often have 2 Medicare cards, and they'll live in multiple households, different addresses. And there's also just a lot of single digit errors, so from either transcribing on the pathology form or however they do it. So I did have to put my data in the penalty box, and I couldn't do a formal evaluation of my linkages. So I'm gonna have to trust some work done by other sources, or hope I come across some better data. The ideas here is that we've got a few unsupervised learning algorithms that we can use. So once you've scored the similarity between the two potential matches, you can do an expectation, an EM, or expectation maximization algorithm, similar to what you use in some of the latent class analyses, and in particular, or you got your clustering algorithms, so your k-nearest neighbors, and you'll know some of these. However, I had to put my data in the penalty box and resort to deterministic methods that are used in this pilot. So unfortunately, I can't showcase some machine learning for this particular project. But so now we are the statistical methods that are used for determining vaccine effectiveness. So we've just used a log binomial model, which is really similar to the odds ratio. So logistic regression from the machine learning world is virtually very identical, very similar model, except you're measuring a rate ratio rather than an odds. And then, as we've talked about, the vaccine effectiveness is just 1 minus that rate ratio. So here, quick, we're going to get to the results. So we did do the linkages, and there was a total of 47 hospital admissions. Now, we reviewed each of these individually, and yes, this all makes actually a lot of sense. So it's a very low hospitalization rate. So it's less than, it's 0.5%, and it's really what we observed in our hospitals. Again, these are COVID-specific hospitalizations, I should mention, because what might happen is you'll have, you know, a 75-year-old woman who has COVID, and as a result of weakness, falls and breaks her hip. So she gets admitted with COVID because of COVID. So we're really looking for the people with admitted due to the complications of COVID, even though you could argue that those were complications of COVID, because COVID will increase your frailty, and the frailty will increase your chance of having a fall or having heart failure if you've got pre-existing medical conditions, right? So the first step is that you also see, so what we don't know is we actually don't know the behaviors of vaccines in our First Nations populations, which are Aboriginal and Torres Strait Islanders. So as you can see here, 7% of our cohort is from a First Nations background. The second circle you see down there, that's just all this is telling you is that this is all Omicron. I don't have any Delta cases in this. Note that we don't sequence every case, it's too expensive, but we do sequence it's about less than 4% of the cases will actually get randomly selected for whole genome sequencing. And what you notice here is that the majority of the delivered vaccines, in particular the primary courses, were Pfizer. People like me who are in health, we got vaccinated very early with the AstraZeneca. And as you remember, there was the complications of the thrombotic complications with AstraZeneca, which really put it on the back burner. And as since AstraZeneca is hardly used at all in Australia, despite its benefits because of the cold chain, you don't need to keep it as cold. So we saw an overall admission rate of 47, and these were both. We had very few in our First Nations population, so only 13% of the admissions were in First Nations percentage, which means they were overrepresented in our sample. You'd expect about 7%. Now, so this is a key question, is this the question that this table is answering. This is what you look at as on the left is you've got your two vaccine brands. Just look at the top two key rows there. We've got a univariate model presented in the first column, and then the multivariate model in the second column. Because I couldn't include the unvaccinated cohort in here, because it doesn't make sense in this model, we're looking at comparing the vaccines, the AstraZeneca. So the base vaccine category is Pfizer. So everything's being compared to Pfizer. What this is demonstrating, so if you look at the 3.49, you see at the top of the multivariate primary course column, that means that persons with AstraZeneca were 3.5 times more likely to be admitted to hospital if they were infected than persons who received Pfizer. It's really clear that Pfizer is a much better vaccine than the adenovirus vector. So adenovirus is what they used for AstraZeneca. It also suggests that the mRNA technology. So Moderna is the mRNA 1273. That vaccine also has very similar outcomes to the Pfizer vaccine. Essentially, it's not different. There's no difference between the two. So importantly is that you can't. Okay, I have to preface this is that if you look at the confidence intervals, they do cross one, so they didn't really find any findings, and this is likely due to very few events. So the events noted is what we only had 47 events, hospitalizations, and that what drives that with that unwieldy confidence interval that you see, but this is consistent with what we're seeing in the literature. Other things that you'd expect, here is that persons who were over 50 years old were more likely to be admitted to hospital. But when you break that down even further, it does get a bit stronger. But that's not the most important finding. The most important finding is this. All right, so this is vaccine effectiveness. This is vaccine effectiveness against hospitalization. So we had 3 vaccine types in that sample. So we had Pfizer, AstraZeneca, and Moderna. And what it found that if you had a primary course, you were 69%. Either was the chance of hospitalization. Okay. Let me start again. Okay, the vaccine effectiveness against hospitalization was 70% for persons with a primary course only, and 81% or 82% in persons who had a booster shot, a booster dose. Now, these were both significant, so this gives me a lot of confidence in these findings. The First Nations finding is not significant, but it's not different from the primary course, and I tested this in some interactions in some other models, and they're not shown here, but I'm fairly confident that what we're seeing here is probably signal rather than randomness. Now, I think it doesn't look like that our First Nations populations react differently than the normal population. However, I can't say that with certainty or with even great confidence, given my the unwieldy confidence interval that I've got there. So I did a sensitivity analysis, changing all those parameters that we had. So, I included people that were partially vaccinated in the vaccination group, just deleted them. I tried different vaccine cutoffs, so 7 days, 14 days, 28 days. And then I changed the time between hospitalization to only really keep certain things. Really, what it comes down to is that what we observed was signal, and the model is relatively insensitive to changes to some of the arbitrary parameters that I chose. Just gives me a bit more confidence. So this is the first estimate of vaccine effectiveness in our First Nations population, and we're reassured. This pilot study demonstrates that yes, it's possible to do this in a real-time basis, because this is all one single page of code, and we can, we could deploy this in a scalable fashion, especially with a deterministic algorithm for all of Queensland, which has 2 million people in it, 2-3 million people. So the Moderna trial, well, this is also important. There's actually really not a lot of information about vaccine effectiveness in First Nations population. There is a Brazil paper that's coming out soon. But, Moderna trial, this is the only quote that I could find in the early efficacy trial that really looked at, ethnic minorities and vulnerable populations. And they did increase some of but they didn't give us a breakdown of how many they had in there. Waning immunity to hospitalization is well known to be 20 to 30% at 6 months. So this is something I could not measure waning immunity. I certainly tried, but my confidence intervals were way unwieldy. And so that's going to be the subject of a future paper. In fact, there's a PhD in this if someone online is interested, or not someone is interested online. The limitations, well, there's plenty of limitations, but I definitely undercalled my hospitalizations because I used a deterministic algorithm. I'm sure that I undercalled it, but that's the nature of data linkage. There were few events. You witnessed my unwieldy or wide confidence intervals, and as I mentioned before, there was no private hospital admissions included, though we don't think there were many COVID-19 admissions to private hospitals, because in Central Queensland, they were often pushed to the public system because the private did not want to deal with them. We didn't include rat tests. Now, if you remember, right at the beginning of January, there was a lot of shortage of rat tests. So it's not like they were very available, but they did sort of loosen up and become available into February and March. And I didn't include there's a local discrete Indigenous community called Warbinda nearby. Great little place. they were managed entirely. Well, our unit managed their outbreak entirely with the use of rats because we needed a fast turnaround time. So none of them were represented here either. And I think from memory, there was actually about somewhere between 4 or 5 hospitalizations that it came from a very small group there. So I think we underestimated some of that in our First Nations populations. Other than that, that is my conclusion. If you want to go away with one figure, is that we probably in Queensland see an approximate 82% vaccine effectiveness in our population. And that's all, everybody. Thank you so much for listening to me and my talk. And I'm absolutely open for questions and discussions.
Thank you, Nick. Any questions?
I don't have any questions. I just thought it was really good, Nick.
Yeah.
Thank you.
That was really good. So did you say like you tried unsupervised learning, machine learning, and it
Yeah. So we are in the process. I'm absolutely doing it. My problem is computational efficiency. So, for example, it works pretty good. In fact, it works in parallel to this. My problem is that I can't do it for the entire sample. If I take, so just an example, we've got 300,000 AIR records. AIR means Australian immunization records. And I've got, so I'll just take a random sample of those 9,000, right? So I've just taken a random sample of 1,000 people from that 9,000 cases. And then what you do is you got to match all the 300,000 with each 100,000 persons there, right? So that's without blocking. So that gives us, like 300 million records, something like along those lines. Then if you just match them based using on a blocking thing like a postcode, so you only match people within a postcode, that brings us down to 44 million records. So I've got a computational efficiency problem, which is probably why I'm going to have to look at doing this in Julie or something else. Otherwise, getting some time on a much larger processor. The issue is that this is Queensland health data, so I have the big data problem. So it's probably going to be changing language, because I won't be able to do this on the fly in real time, because we've got to merge this in real time with all these records. If we're going to do this for all of Queensland, we've got 2 million plus 2 million AIR records, plus we've got we're going to have 500,000-600,000 infections since the beginning. So so I have tried it. It works. It looks good. It's just not, I haven't been able to evaluate it to tell you that, I've got, I can't, I was hoping to evaluate it for this presentation actually 2 weeks ago. And that's why I put my data in the penalty box, because I was very unhappy to see that my Medicare numbers were not giving me good true matches. So that's why I was like, I had to put my data in the penalty box, and we had to reevaluate. Yeah.
You're not the first person to come across that problem, Nick.
Yeah. But I had a lot of confidence in the Medicare number, because I thought it might have been tied to billing. And when it's tied to billing, you get some good accuracies. But then that
happens.
Yeah. But anyways, there is the PhD for this is up. Oh, fortunately, sorry, the Statistical Services branch of CDB, of Communicable Diseases branch in Brisbane, they've already done the linking of COVID cases to NOx, to the immunization register. So now I don't have to, that's one step I don't have to worry about. We can pull that and we can merge it with just the next step is the hospitalization data set, which I hope might be a little bit better, easier to do. So So there is a PhD in this. This is what we were talking about, Emily, is scaling this to do this for the entirety. This was of Queensland, and that's what that grant we wrote together was all about for that hero thing is this, but at scale.
Yeah, I think it'd be really interesting work.